And now I would like to give the word to Maria. I'm very excited that we have you with us here today, Maria, and I look forward to your talk. You're an associate professor in AI, artificial intelligence, at the University of Bergen in Norway. And I also know that you're head of research for the Information and Science Division. And you're also vice chair of the Norwegian AI Association and a member of CLEAR, which we will hear a little bit more about. So definitely heavily engaged in AI. And of course, this is a topic that I think it's on most people's lips this day, definitely when we're talking about digitalization in the bioeconomy. And it's also the focus when we're looking at different policy, EU policy initiatives, etc. But I guess the question here that we will try to answer, Maria, is what does AI actually do and what does it do well? Maria, please, the stage is yours.
Thank you. So I'm gonna just share my screen here. Okay. And right. So hello. Thank you for that very nice introduction. It's always a pleasure to give the inspirational talk. So thank you for being here today on this talk. I have been a researcher in AI for at least 10 years now, and my area of expertise is collective reasoning and ethical reasoning. But today I would like to give you like the short general tour of AI. So I would like to start not with an overview as it is typical, but with some disclaimers. We are surrounded by conversations and expectations of AI, as you already mentioned. And I have a suspicion that sometimes it makes it very confusing for people to keep track of the different tech purposes and terms that are being put forward. So therefore, disclaimers. So first, what is AI being made for? Why are we doing this? With the Silicon Valley exerting such dominance in the media today, we might be tempted to think that AI is there to stalk us on the web and track us around and to sell us more commercials. This is not the goal of AI. This is just the business plan of some companies in the US and China. Both AI and machine learning are mentioned often together. These are not synonyms. Machine learning is one of the areas of research and application of AI, and it is definitely not the only area. And it is a pity when people just equalize them. Deep learning, it's also put into this mix. And somehow when people say deep learning, they think that this is something different and much more intelligent. Deep learning is a special type of machine learning, which is not called deep because it is more intelligent, but due to historical and design reasons. Lastly, AI is not the same as big data or data science. These are also sometimes thrown together. AI is used in data science and data science is used in AI, but these are two different fields. And one last disclaimer, a lot of people I talk about get very much anchored in this idea that AI is something that big tech companies, huge tech companies, I should say, develop, and that we can just take their products and apply them. And this is what we do in research, in fact, everywhere else outside of the Silicon Valley. This is not true. I'm going to give you the big picture of AI, but from the bottom up. And this talk may seem basic, but I deliberately built it in that way so that you can take the root of AI and I can show you what the essential capabilities are, which can be then taken and understood, I hope, by everyone to serve their own production and development purposes. So let's go. What is artificial intelligence about? So artificial intelligence studies how can we build intelligent behavior in computational systems. And of course, for this purpose, how can we understand what intelligent behavior means for computational agents? I have here this timeline to show you. Of course, you cannot see the details. You have to look at the slides that were uploaded for the details, but I wanted to put it here on the slide anyway to demonstrate that artificial intelligence has been around since 1956. We have an inception date for it. And it is very much a developed field, but what is specific for this field perhaps is that the excitement of what the field can do, the promise of what the field can do, this boom we have seen that before. In fact, this is the third time we're going through the boom of AI. And in between these booms, we have had these winters which have come about as a consequence of people having a very high expectations, then being let down and withdrawing funding. So typically when you take somebody who does research in AI and ask them about AI, they are very couched and conservative to tell you about the prospects, because we have learned that to exalt expectations means to lose funding. And of course, we hope that this is not the case this time. So what is the, I told you that we were not building AI to sell commercials online. Then what are we actually building it for? We build artificial intelligence to automate those jobs that people are currently doing, but which they would rather not do. Jobs that are dangerous, jobs that damage the human body or the human mind or both, or jobs that are simply boring and repetitive. So I have to say my knowledge of agriculture is very, very limited, but one of these jobs that I do know that nobody really wants to do is, for example, picking strawberries or picking raspberries. So jobs like that. Technology has been used to automate tasks for a long time, particularly in agriculture, I would say. These are very interesting examples there. And these are two cute pictures of how automation of, well, in my opinion, cute, how automation of movement, for example, is executed. The specific type of automation we're talking about in artificial intelligence is how do we automate cognitive tasks? So to show you how we go about this, I picked one cognitive task, and I will show you how AI goes about its automation. And the task I picked is reasoning. Reasoning can be seen as the process of using rules that connect cause and effect. Why did I pick reasoning? Well, it's somehow what we intuitively associate with intelligence. Think about how a monkey trap works. So you put some food in a box with an opening that is big enough for the monkey to slip its paw in, but it is too small for the food to be taken out through that opening. Now the monkey sees the banana, puts the paw inside, grabs the banana, and tries to run away, but it can't. Because the monkey cannot connect the effect, I cannot run away, with the cause, I'm holding on to this banana. And we are thinking about, well, the monkey is not very smart. There are three types of reasoning that involves this process of using rules to connect cause and effect. If we are given some facts and some rules, and we want to find answers that are entailed by these facts, then we are talking about deductive reasoning or deduction. Here's a little toy example of a problem that requires deductive reasoning. So we have a social situation in which a married George is looking at Jane, and Jane is looking at an unmarried Jack. Now we are some kind of a prude here who wonders if there is someone married looking at someone unmarried. And to find out, the type of reasoning that we use is deduction. In this particular case, feel free to call the Spanish Inquisition, because the answer is yes, there is somebody who is married looking at someone who is unmarried. If instead, we are given some desired state of the world and some rules, and we want to know what has caused this state, how is this state possible, we need to use abductive reasoning to find out, or abduction. Now this sounds a little bit weird, but you have seen this type of reasoning every day as well. So solving a Sudoku puzzle, for example, requires abductive reasoning, because what we want to know is which were the numbers that were deleted here, what completes the puzzles. Even more familiar, this is the type of reasoning that Sherlock Holmes uses when he solves cases. Lastly, let's say that we have observed some phenomena and we would like to know if they are connected. So which are the rules that connect them? And to find these rules, then, what we use is inductive reasoning or induction. So I have here a little collection of people I took from this lovely book I use in my classes for teaching. I have their age, how many cars they own, if they own a house, how many children they have, if they are married, and if they own a dog. And I wonder whether this information of the people somehow connects with whether a person will choose to buy a boat or not, for whatever purposes. Or I have a bunch of handwritten digits, and I would like perhaps to teach somebody how to write these numbers. So I know that the first row are all the digits of 0, the second are 1, and so on. The last row is digits of 9. And the question is then, of course, what makes the 0 a 0? Or what is the rule that identifies this squiggly line as 0 rather than it being 8? And to develop that rule, what I use is inductive reasoning. This type of reasoning, induction, is what machine learning in artificial intelligence is actually about. The rule that connects the observed phenomena we call a prediction model in machine learning. The cause we call a training set, and the effect we call a class or a label, a set of classes and labels, one for each element of the training set. When we talk about finding the prediction model or training a prediction model so that we can predict which class should be assigned to a phenomena, we talk about supervised learning. All the great awesome achievements of AI today, such as image recognition or speech to text or automated translation, these are all implemented using supervised learning. These are all examples of supervised learning in action. Some other types of machine learning in play, if we are not able to separate what are the cause and what are the effect, but we would still like to find out some pattern in these phenomena, what we are using is unsupervised learning. Lastly, the core approach used to build the exciting new developments such as AlphaZero-Go is so-called reinforcement learning. The problem here is the same as in supervised learning. We are using inductive reasoning. The difference is that we are not given one set of labeled data to build one set of rules to match them with, but the set of rules is changed dynamically with each new pair of cause and effect considered, which here are actions and their outcomes respectively. So actions in a current state and the outcome that we get. And the rules are then put in place to find out which actions lead to a desired state. This type of reasoning we typically see in playing games. Now you say, well, okay, what is the big deal? Making inferences from data, I can do this with statistics. So I can find this linear model, for example, and then determine the W's, how much each of these features impacts the effect, which is whether somebody bought a boat or not, and do, for instance, linear regression to this. Let me build this linear model into a neural network. We feed the value of a feature multiplied with its weight W to a neuron unit here on the left. The neuron is an activation function, which is like a valve. It releases a value once the input it receives is high enough. A linear model only considers the features one by one. So how much does X0 has impact on Y, how much the X1 has individually impact on Y. A neural network, however, can consider what effect an arbitrary combination of features has in determining the label of an object. So to unleash this power, what we do in a neural network is we add more units between what is the input layer and the output layer of units. This additional layer is called a hidden layer. And we can add as many of these hidden layers as we like. Training a neural network is figuring out what values should these W's have, again. But of course, now we do not have 5 weights to learn, but of course 54 in this particular toy example. Machine learning with neural networks that have at least one hidden layer is called deep learning. So this is where deep learning comes from. Now, I would like you to pay attention to something. We know what the inputs to the input layer mean when we are only using these first 6 in this case, inputs. But we no longer have an intuitive understanding of what features does a net neuron from the hidden layer end up connecting. Especially, this intuition is lost when there are several hidden layers. So each of these neurons in the hidden layer, it takes an arbitrary combination of features into account. When people talk about not knowing what the neural network does, this is what they are actually talking about. This intuition is completely lost when what we are having on input is some kind of an image, which we are trying to recognize what is on the image. The input layer of a network that tries to make inferences about images is fed the pixels of the image. So in this particular case, this is 28 times 28 in grayscale. Or if this particular picture is 536 times 536 pixels times 3 values for each of the picture. Now, as the number gets larger and larger of input units, we need more and more examples to find the weights effectively, these W's that the number of W's increases even more, which means that we need more and more pictures to train the network with, which is why machine learning guzzles such large quantities of data and sometimes gets identified with big data. So the question then, what are the limits? There are some limits that come from the type of reasoning and how we have modeled reasoning. When we use deduction, it is important that all the rules that are required are specified. Not even the most obvious or commonly known rule must be forgotten. And to show you how easy it is to forget to enlist the obvious, in the example in the previous slide, I omitted one very crucial rule that allows you to solve the puzzle. And you will see it here. In abduction, we can have multiple causes having the same effect and not having enough information to choose the right cause. So for instance, this Sudoku puzzle is solvable, whereas this Sudoku puzzle is not solvable. Some numbers here are missing to make it unsolvable for this example. It's not solvable because it has multiple solutions and we wouldn't necessarily know which one is the right one that we're looking for. In induction, the problem is that induction always discovers correlation between phenomena, not causation, and then correlation can exist among the most weird of things. How good your inference rule are depends very much on which examples you have taken to work with. And even if you're very, 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 very careful, there is always that danger of an example that is rare, which hasn't occurred when you were finding your induction rules, but will nullify all your inferences when it does occur. So I would like to then look at immediate limitations of artificial intelligence, not just of reasoning. If I zoom out of this reasoning picture, I will find that cognition is not just reasoning. Of course, we already knew that. We are framing the problem very cleanly in these slides and in AI in general, but how do we get to this clean reasoning problem? And the answer is a lot of human labor. So we need a lot of observations to build these causes. We need to encode all of the elements of reasoning in a language that can be fed to a computer. We need to interpret the computer generated answers for people to be able to use. Of course, we need rules in deduction and in abduction. And these are rules that need to be built by domain experts, which can be very, very time consuming and expensive. Automating each of these additional cognitive tasks is a separate sub area of research in AI. And a lot of these tasks we still don't know how to automate. But of course, if you want to know what the latest research news are in AI, there is a beautiful new resource that just came about, and you can check out this webpage where researchers report on new research in AI. For those of you who subscribe to the Superintelligence Curiosity Fan Club, I want to also discuss what the really, really hard limitations of artificial intelligence are as we see them today. I will do this using visual means and a machine learning example, but this is a general problem that spreads out through the entire AI. Supervised learning today is making great progress identifying features of pictures that depend on its pixel. So identify the picture of the malignant tumor. We're making great progress in things such as that. However, let's say that I have this picture instead, and looking at these pictures, you will see that on the left we have 6 images that have something in common. They're all convex, and on the right we have 6 images that also have something in common, opposite to the left pictures. They're concave. How can we actually have a machine that recognizes this, what these pictures have in common and what they have, how they are opposite with the pictures on the other side? We do not know how to solve this problem in artificial intelligence, and we have been trying since 1956. And to figure out superintelligence, and when people say, oh no, superintelligence, we don't know whether we can get there. To have superintelligence, we need to be able to solve problems such as this as well. So question, how do we rise above the limitations? So Maria asked me to talk a little bit about Claire, and Claire is here as a network is perhaps one answer about rising above limitations in artificial intelligence. Now, typically when people talk about artificial intelligence, Europe is compared to AI in China and in US, and we are not seen as a front runner. However, the interesting fact is that we actually publish the most research papers in basic research, and this is most compared to both China and the US. However, our problem is that we are splintered. We are groups, little groups of researchers spread out through many countries. And as such, we are too small to get notice. And therefore, we have decided to come together and make this network, CLARE, which is a confederation of laboratories for artificial intelligence research in Europe. This is an organization that was created by the European AI community with the purpose specifically of strengthening European excellence. And we like European excellence that also takes people into account. So that makes values for people, not just for companies. CLARE wants to put these splinter groups in EU together, first in terms of infrastructure and eventually in an institution like CERN. Now, of course, you can find all the information about CLARE on this webpage, just a little bit of facts. It was launched in 2018, and now we have the support of more than 3,300 people. The vast majority of the support comes from the European AI community, both academia and industry, research and innovation. We have the official support of 9 national governments, and we are actively working on increasing this number. There are administrative offices in The Hague, Saarbrücken, Prague, Oslo, and we are working on Rome, Brussels, Paris, and Zurich. So currently what CLARE is working with is of offering guidance and coordination for EU AI public-private partnerships, offering guidelines for national strategies. We're trying to have as many national contact points as possible, so one for each nation. People are working on incorporating CLARE in Brussels and obtaining some seed funding to continue building towards our goal, which is one large research center that connects all of the researchers in Europe. As I said, you can find all of the information on CLARE on the webpage, but we are also having a very active Zulip community, so you're free to join that one as well. Okay, I hope you have a lot of questions for me. If you don't manage to ask all of your questions today, please feel free to get in touch with me. My contact details are available and I'm easy to find online. So thank you.
Thank you so much, Maria. That was a lot of, I see someone doing applause. I will, since I'm not muted, I will give you an applause. Thank you very much. I think that was very, very interesting and also quite mind challenging. I wanted to say early in the morning, but I don't think I can blame early morning anymore. But I will definitely go through that again and see if I can pick up even more from your presentation. And thank you also for reaching out. And I guess if anyone wants to get in contact and ask specifically in a more private room some questions, they could get in contact with you. Is that okay?
Yes, please, of course.
And I know you have your own website, so you're definitely easy to find.
Yes.
Yes, and I would like just first to ask a question about this CLARE network. So do I understand it correctly that this is both sort of a network, a virtual meeting place, but you also have some sort of physical place?
Yes. So the network does not have official employees, but there are offices which are manned by a combination of volunteers and funding that comes from all kinds of different types of places. So the virtual network exists in which everybody can get in touch with everyone else, but there are some physical offices that are maintained, particularly for formal contact with governments and industry, in people that want to get in touch and have a meeting and have a conversation one-on-one. So we have those. We have an office in Oslo. I know that one is open, but the idea is to have one office in each country in Europe eventually.
Thank you. I think that's interesting to learn how a big network or organization such as CLARE is organized, and hopefully that can be a bit inspiring, definitely for me and other stakeholders engaged in the testbeds in digital bioeconomy, to see how we can actually organize ourselves on a larger scale as well.
Yeah, I think with CLARE, it was very much, the time was very right because it came together very, very fast. So it was very fast to obtain support from people. People really wanted this to happen. And there has been some excellent groundwork that has been done mainly by volunteers who put it together, right? So we are the largest, in a way, kind of like a trade network in effect. And we hope that we continue being successful in putting people together and gaining funding so that we can have this dream of a joint hub facility, European AI in place.
Thank you, Maria. And your contact details are here in the presentation as well, if anyone wants to get in contact. And I can see that Lars here is putting his thanking you for a nice presentation and actually making AI a little bit more understandable.
Sorry, I see a question here that no Nordic country is supporting Claire. There is informal support, but what I mentioned on the slide is formal support from the government with a letter from the ministry and everything. So the works are in place to get this from Norway, and we are getting very strong signals that this will happen, but I don't know what the situation is with the rest of the Nordic countries. Okay,
thank you,
thanks.
and thank you for your question, Henrik. On that note, thank you to Maria, and we will move on to the testbed presentation. So thank you very much, Maria. It was very great having you with us.
Thank you.